Okay, we're looking at 4.3 here, linearly independent sets and bases. And I just want to start by sort of reminding you what linear independence means, which we saw in section 1.7. So there's a whole section about this in 1.7 if you want to remind yourself. Maybe go back and take a look at that. But in that section, we had this definition. So this is from section 1.7. And it's the formal definition of linear independence or dependence. So we say a set of vectors is linearly independent if the equation x1, v1, the linear combination, basically, if all linear combinations of those vectors equaling 0 has only the trivial solution. So if you think back to the section, what we did here is we solved the homogeneous equation to look for linear independence, right? And so if this equation has only the trivial solution, we have linear independence. And so that means that if that same equation has a not zero solution, that means we have linear dependence, right? And so let's think about what this means. This means that all these c's are not zero, right? So we can find some non-zero weight of the vectors that sum to 0. And so we can rewrite that. We can solve for any one of these vectors. Like if I solve this equation for VP, for example, I would subtract everything over to one side and then divide by CP to get VP by itself, right? And so this is going to be this. They'd be subtracted, so they'll all be negative. And so this is just sort of showing you how if you have a non-zero solution to the homogeneous equation, that means each vector in that set is a linear combination of the other ones. And so that leads directly to this theorem right here, the first theorem in this section, which tells us an index set of vectors v1 through vp, with one of them not being 0, is linearly dependent if and only if one of them is a linear combination of the ones before it. Just like this, right? This is showing how one of the vectors is a linear combination of the ones before it. And so that leads us, that's an important thing to remember and to realize, because we don't just want to be able to set an equation equal to 0 and see if the homogeneous solution has a solution, right? This only works for vectors in Rn. If we have vectors not in Rn, like the example down at the bottom of this page, then we need to use this definition directly. Right? And so that's what it says right here. Previously, we had approached these problems by looking at solutions to the homogeneous equation, but in general vector spaces, like the ones down here, we can't always write things in a matrix, and so sometimes we have to use this definition and this theorem to see whether or not something's linearly independent. For example, here's a set of 4 vectors, p1, 2, 3, and 4, where they're polynomials, right? So p1 is the polynomial 1, p2 is x, p3 is x squared, p4 is this degree 2 polynomial, 2x squared minus 6x plus 4. Let's show that the set is linearly dependent. And so think about, so let's use this definition. Can we construct one of these vectors, p1 through p4, by doing linear combinations of the one before it? So take a second and maybe think about that. And maybe I'll just give you the hint that, yes, we can, not can we, so we can construct P4 using the ones before it. So we can construct P4 using linear combinations of P1, P2, and P3, right? Because P1 is just a constant, so if we multiply this by 4, we get the constant in P4, right? We have x with P2, so we multiply this one by -6, and we get the -6 here. And so P4 which is 2x squared minus 6x plus 4, we can use the different P1, P2, and P3 to get these, right? For the 2x squared, we'd use P3. For the 6x part, we'd use P2. And for the 4, we could use P1. Specifically, P4 is 2P3 minus 6P2 plus 4P1. Right? So P4 is a linear combination of P1, P2, and P3, which means it's linearly dependent by this theorem and the definition at the top of the page. Right, so since P4 is a linear combination of P1, P2, P3, the set is linearly dependent. So the set P1, P2, P3, P4 is linearly dependent. Because 1, P4, is a linear combinations of the other ones, P1, P2, and P3. Maybe take a second and think about what could we remove from this set to make it linearly independent. Is there a vector? Could we remove one of the p's to make this linearly independent? Well, it turns out if we remove any of the three of them, it would become linearly independent. So in this particular case here, removing any of the p sub i's creates a linearly independent set. Like if we remove, first of all, if we remove P4, these P1, P3, and P3 are very clearly linearly independent. But even if we remove, say, the 1, you're never going to be able to get this one because this one's got a 4 in it, right? You're never going to be able to get rid of the 4. You can't get this one because this one, you're never going to get rid of the 4. Or you can't create this one because you're not going to be able to get a constant. And so removing any one of those is actually going to create a linearly independent set, interestingly enough. So this is just a review of what linear independence is, mainly because the thing we're about to talk about, which is a basis, requires linear independence. And so we just want to remind ourselves that linear independence or dependence depends on whether or not anything in the set is a linear combination of the other things in the set. So just keep that in mind as we consider this definition right here. This is the definition of what it means to be a basis. And so let H be a subspace of some vector space V. An index set of vectors B1 through BP, which we usually represent with the Greek letter beta, in V is a basis for H if these two things are satisfied. So if the set beta, so the set of vectors, is linearly independent, so that's why we just talked about linear independence, and if the subspace spanned by that set coincides with H. In other words, H equals the span of the set. And so these definitions is what it means to be a basis. So if you're asked if something is a basis, you want to see whether or not these two things are satisfied. And so I like to usually rewrite each one of these things in different terms to try to re-explain them. Hopefully you've seen from the invertible matrix theorem, all this stuff is tied together and can be rephrased different ways. So let me try to rephrase these things. So this set being linear independent, that means that no vector in the set is a linear combination of the other ones. That's what we saw in the last set. Another way to sort of say that, the way we talked about it in the linear independent section in 1.7, is that you can't construct any of the vectors using the others. So no vector can be constructed using the others in the set. So go back to 1.7 and maybe remind yourself about that if that doesn't sound familiar. That's sort of how we talked about linear independence in that set. The second one I feel like is kind of phrased a little bit strange here. The subspace spans by beta coincides with H, that is, H equals a span. In other words, the whole point of something being a basis is that you can construct any of the vectors in that set. And so H equals the span of the vectors means that anything in the space H can be written as a linear combination of the values in the basis. And so another way to say number 2 would be that all of the vectors in H, in your space that you're talking about, can be constructed using a linear combination of the vectors in beta. So if this still isn't sort of resonating with you, I think it's helpful to think about this non-math example. I think this is a really, really great analogy to think about. So the periodic table of elements forms a basis for the natural world in the true sense of the word basis. So think about the periodic table, right? So you have like hydrogen and oxygen and all these elements on there that are as basic as they can get, right? You can't break, in other words, when you break down matter into smaller and smaller pieces, the smallest pieces that you could get is the periodic table. And so in that sense, they're linearly independent, right? Because you can't take linear combinations of anything on the periodic table and create hydrogen, for example, right? Hydrogen is just hydrogen. You need hydrogen to make hydrogen. And you can't take linear combinations of anything else to create oxygen. Oxygen is just oxygen, right? It's as basic as it can get. So all the elements are linearly independent in that they're the smallest particle they could possibly be. And everything in the natural world is a linear combination of those elements. So the periodic table spans the natural world, right? If you want water, you take H2O, two hydrogens and one oxygen, for example, right? So a linear combination of hydrogen and oxygen gives you water. And anything in the natural world is a linear combination of the things on the periodic table. And so everything on the periodic table is linearly independent, and everything in the natural world is in the span, right, linear combinations of the periodic table. And so if you're ever sort of struggling to think about what a basis is, just think about the periodic table. Linear independent, you can create anything in the natural world using them. And so I hope that helps. I'm happy to clarify that in a conversation if you want, but let's look at an implication of this mathematically. And so it turns out that the E1 through En, the columns of the identity matrix, actually create a basis for Rn, and it's actually called the standard basis. And so when you see someone refer to this E1 through En as the standard basis, or if you hear someone say the standard basis for Rn, that's what they're talking about. And so let's look at that. Let's look at a specific example like in R4. So for example, beta equals E1, E2, E3, and E4 forms a basis for R4. And again, remember, E1 is like there's a 1 in the 1 spot in the first entry and 0 is everywhere else. E2 is there's a 1 in the second spot. So like this, for example. E1 is 1, 0, 0, 0 because we're in R4, so they have 4 elements. E2 has a 1 in the second spot. E3 has a 1 in the third spot. And E4 has a 1 in the fourth spot. And so hopefully you can see that like these four vectors, can be used to create any vector in R4, right? Whatever you want in the first spot, you multiply this one by that. Whatever you want in the second spot, you use this one to create it. Whatever you want in the third one, you use this one. Whatever you want in the fourth spot, you use this one. And they're linearly independent. But if you actually want to show this, you can't just like say, oh, it's obvious. You actually have to show that they're linearly independent and they actually span the space. And so, I'm trying to just mess around with the light here. Maybe that's a little bit better. Sorry if it was too bright before. So let's actually go through these two things. Let's show that these things are linearly independent, and let's show that they span the space. So we want to show linear independence, which means the homogeneous equation has the trivial solution. And we want to show that there's the pivot in every row, which would mean it spans the space. And so let's take these vectors and put it in a matrix. It becomes the identity matrix, of course. And so I've just taken E1, E2, E3, and E4, and I'm trying to see whether or not they're linearly independent and whether or not there's a pivot in every row to see if they span the space. And so let's reduce this. RREF. Well, it's already reduced, right? It's the identity matrix, and so it doesn't get any more reduced than that. But if it was a group of 3 other vectors, we would have to reduce it and see whether or not there's a pivot in every row, whether or not there's a free variable. And so when we reduce it, we see that there's a pivot in every row, and there's no free variables. And so these are linearly independent and span the space, right? So there's no free variables, and we see that there's a pivot in each row. And those are the 2 things we need to answer the question about whether or not this is a basis. Because when I go back up here, we want to show those 2 things, 1 and 2. So I'm going to write those 2 things down here. Number 1, is it linearly independent? Is this set linearly independent? Question mark. That's the first question. And the second question is, do the vectors span R4? Well, they're linearly independent because we have no free variables, so we get the trivial solution. So yes, because there's no free variables. In other words, we only have the trivial solution to AX equals 0. And do the vectors span R4? Well, there's a pivot in every row, so yes. So yes, because we have a pivot in each row. And so, since 1 and 2 are satisfied, we have a basis. So since 1, we have both our things satisfied. E1, E2, E3, E4 forms the basis for R4. And so, anytime you're given a set of vectors, a very common question is like, here's a set of vectors. Is it a basis for a certain space? You want to look through those 2 things. You look whether or not they're linearly independent and whether or not they span the space. And all that means is putting them in a matrix and row reducing and looking for free variables and pivots in every row. Right? Those are very common things we're looking for. And so, so those are the kind of things we're thinking about. Now, this is an easy one because the reduced form was the exact same as the original. But like on the next page, the question is, do these form a basis for R3? And you can't just tell by looking at those 3 things. And so in that case, you actually have to do a little bit more work on there. Okay. So notice, what this means then, since this is a basis, it means that they're linearly independent. In other words, you can't boil these 4 things down to anything more simple. They're as simple as they could possibly get in order to span the space. That's sort of what linear independence means. And any vector in R4 can be created using linear combinations of those things. And so, for example, let me show you a general vector. A general vector in R4 looks like A, B, C, D. I'm sorry that got a little sloppy. That's supposed to say A, B, C, D. Let me just rewrite it. It's going to be worse. Can you read that? Hopefully. It says A, B, C, D. Well, if you want to get something, whatever you want in the first spot, you multiply that by E1. Right? Because the A will multiply the 1, and then it'll go in the first spot. Whatever you want in the second spot, you multiply that by E2. That'll end up in the second spot. Whatever you want in the third spot, you multiply by E3. Oops, that should be a 1. And whatever you want in the fourth spot, you multiply by E4. So you can recreate any arbitrary vector in R4 by multiplying A times the first one, B times the second, E2, C times E3, and then add it to D times E4. That's sort of the goal behind these basis things. You instead of, if you want to talk about R4, instead of having the whole space of R4, you can just talk about these 4 vectors, because these 4 vectors can be used to represent any vector in R4. So it's more simple to sort of just include these things. These things generate the space, so to speak. It's kind of like if you were going to start a brand new world, you could either like go through our physical world and copy everything if you could, or you could just take all the elements, right? Copy the elements of the periodic table and then use that to regenerate the entire world. And so you can use bases to sort of regenerate spaces or represent everything in the space without actually having everything there, right? Because they represent everything in the space. Okay, and so as I mentioned, a very typical question that you sometimes see is like, is this a basis? Is this a basis? And so here's two examples. Determine whether or not this is a basis for R3, determine not whether this is a basis for R3. And in both cases, what you need to do is put the vectors in a matrix, row reduce it, and see whether or not you have free variables or whether or not you have a pivot in each row. And so that's what you want to do in both these cases. And I'm going to kind of leave this one up to you. I'm going to sort of set this one up, but you should already be thinking about what the answer might be. So I'm going to put these vectors in a matrix and row reduce them both, and then give you a second to think about what the answer is. So I'm taking these vectors, let me do it in this order, and I'm putting them in a matrix, and then you want to row reduce it. And if you row reduced it, you should be sure you can do this yourself, but this is what you would get. And I'm going to do the same thing with this one down here, just so you can, just to save you some time. So this one, we put these things in a matrix, and you RREF them. You don't need full RREF. You just need REF technically, but I'm going to give you the full version here. Okay. And so the question for both these is it a basis for R3? And so in both cases, you want to be thinking, is this matrix, are these things linearly independent? Question mark, right? And then the second thing you should be thinking is, do the vectors span R3? Right? In both cases, we should be thinking that. So I'm just going to sort of write that down. You should pause the video and think about that right now. Are they linearly independent? Do the vectors span R3? I actually already have the answers written down. And so again, that's what you should be thinking on both these cases. Are they linearly independent? Do the vectors span R3? I'm going to just put the answers up here and walk through them in just a second. And give you, you can pause the video and give you a chance to write them down. And so just pause the video right now. You've got the row reduced form of each of these matrices. You should be able to answer both these questions. Go ahead. Pause it. I'm going to take this one away. Hopefully you pause the video and you're thinking about this. And then I'm going to put the answers up right here and walk through them. So, are they linearly independent? Well, if we took the matrix and we row reduced it and set it equal to 0, AX equals 0, we'd have only the trivial solution, right? There's no free variables here. Right? When you row reduced it, we have no free variables. And so that means the vectors are linearly independent. Right? That's sort of how we figure out linear independence. We look for free variables and see whether or not there are any. No free variables, not linear. That means it's linearly independent. So check. We have linear independence for this one. The second part, does the space span R3? Well, there's a pivot in every row, so yes, right? So we have a 3 by 3 matrix, there's a pivot in every row, and so yes, the vectors span R3. It's kind of like if you wanted this to equal A, B, C or something, you get the first answer from this row, second answer from this row, and third answer from this row. So it doesn't matter what A, B, C are, you're going to get an answer for each one. So since both those things are satisfied, right, we've got linear independence, we've got a pivot in every row, check there too. We have both things satisfied, and so we do have a basis for R3 in this case. Now, I think this is worth mentioning that this is kind of interesting, right? Like the one on the last page should have been kind of obvious that this was a basis for R4. And, the standard basis for R3 would be E1, E2, E3. So it would be like these three vectors without the last row, right? And so that's kind of an obvious one for R3. But it turns out any vector in R3 could also be written as a linear combination of those three things. That's interesting, right? You wouldn't have guessed that probably without sort of doing this analysis. So any vector in R3 is some linear combination of those three things. Kind of interesting. Now notice, we've got three of them. You need to have at least n vectors to span Rn. And so the second one is kind of like automatically a no, because when you row reduce it, you're going to get a row of zeros because you don't have enough vectors, right? In other words, you're not going to be able to span the space. You're not going to be able to span R3 with only 2 vectors. You need 3 vectors to span R3. And so, but when we look through it, do we have linear independence? Well, it turns out we don't have any free variables. And so yes, we don't have any free variables, and so actually we do check off box number 1. So no free variables. So the answer to number 1 is a yes. The other way to think about that is when you multiply this one, you can't multiply the first one by something to get to the second one, right? So the columns are obviously not multiples of each other. So we obviously have linear independence. So number 1 is a check. We don't have a problem with number 1. It's that we don't have a pivot in every row. Right, so our reduced form here only has a pivot in the first and second row. We're missing a pivot in the third row. And so no, A does not have, A only has 2 pivots, and not 3, which means we don't span the space. In other words, if we wanted this to equal some random A, B, C vector in R3, we could get an answer for the first one, an answer for the second one, but the third row is going to end up being inconsistent because we don't have a pivot there. And so this one is no, because 2 fails, right? So 2 fails. So the set is not a basis for R3. Okay. Please check in with me and let me know if you have any questions about that. I'm happy to look at that again. Let's go on to the final page of this section, which just tells us a little theorem here. So let's take a look at what this theorem says. The spanning set theorem. So let's say we have a set of vectors called S. So S is V1 through Vp, and it's some set in vector space V. And let's say that the span of V1 to V3 creates set H. If one of the vectors in the set is a linear combination of the other ones, then we could remove the one that's a linear combination and it would still span H. Right? In other words, it's like if one of them is a linear combination of the other one, we don't need that one because we can just recreate it using the ones that it's a linear combination of. And so that's one thing. The other thing is, if H is not just the 0 set, then some subset of that one is a basis for H. And so the way I would think about this one, I feel like it's a little bit confusing the way it's written. The way I would think about the IE, if you have a linearly dependent spanning set, so the space spans the set, but you have too many elements essentially, then you can remove some of them to create a basis. You can remove the dependent vectors to create linear independence, which will create a basis. So again, it's kind of like if you have too many vectors, so that, hey, you got part 2 satisfied of a basis, right? So it's like you can span the space, but you don't have linear independence. It's saying you can remove some of the ones that are linear dependent to actually span the space. And we kind of already saw that one on the first page, that kind of idea where we saw it said like, hey, this set is not linear independent because P4 is a linear combination of the first 3. But what I had said was, well, you can remove one of them, and then you would have a linear independent set. And so in this case, you would have a linear independent set, which it doesn't necessarily span the set, but it's sort of that same idea. And so that's sort of the idea here. It's saying if we have too many vectors, we can remove some to create linear independence, which will make a basis. And so that leads directly to this theorem. So this, what I'm trying to say here is theorem number 5 kind of leads directly to theorem number 6. And so theorem number 6 says the pivot columns of a matrix form a basis for the column space. So remember, col A, that's from the last section, maybe, I think it was the last section. This is the column space of A, which is all linear combinations of the columns. So linear combinations of all the columns. And so it's saying, like, if you have too many of them, in other words, if some of them aren't linearly independent, you can remove some of them, and then the ones you remove, you don't include, and the ones that you get rid of, right, the ones that you keep, I mean, form a basis. But there's kind of a key thing about this. So, you know, here's the question, right? So consider this matrix. Let's find a basis for the column space. So we want to figure out the pivot columns here. And so we're going to row reduce this to figure out the pivot columns, but then we're going to go back to the original matrix and choose those columns. So that's what it says in the note. To find the pivot columns, you row reduce the matrix, but then you go back to use the original matrix and the original columns to form the basis. So it's pretty straightforward. You'll see what I mean here. So here's A, right? So we want to figure out which ones are the pivot columns. And so let's row reduce this one. So I'm going to do the RREF right over here. And when I row reduce, you get this matrix. So that's the reduced form. And then you can figure out the pivots, right? So the pivot in the upper left, and then you go down right, and this is the pivot right there. So these are the pivots. And so there's two pivots. And so, you know, it's kind of saying like, the way you can think about this 1 and this 2, it's saying like the second column is 2 times the first column. And you can see that here, right? If you multiply the first column by 2, you get the second column. This is a slightly more complicated sort of collection here. It's saying like 4 times the first column plus 5 times the third column, excuse me, give you the fourth column. So if we did like 4 times this, it'd be, I'm sorry, so 4, this is telling us 4 times, let's see, how do we do this? 4 times the first column, right? 4 times the first column plus minus 3 times the second. Would that make sense? Minus 3. I'm having a hard time thinking about it, but this sort of tells us the relationship that tells us the linear combinations of the columns. So basically it's telling us that like the second column and the fourth column aren't needed because they are linear combinations of the first and the third. I'm sorry, I'm having a hard time thinking about how that works off the top of my head. I should have come up with it beforehand, but the idea is we can delete the second and the fourth column, and then the first and the third would become our basis. So I'm going to write some of that down here and then re-explain. So for a basis of the column space of A, we need 1 linear independent set, and 2, we need the vectors to span the column space. Well, 2 is going to be true automatically because the definition of spanning the column space is linear combinations of the columns, right? So I hope you agree that like 2 is going to be true just by definition. So it's true because the columns of A automatically span the column space by definition. But what we see here is that 1 is not true. So the columns are not linearly independent because we can automatically see like, so number 1 is not true. We don't have linear independence because, for example, column 2 is 2 times column 1. right? So we're doing a linear combination of column 1 to get column 2. Oh, and I just realized the column 4 one. And then column 4, this is telling us this 4 or 5 thing is what's confusing me. This is saying column 4, column 4 going to here, is 4 times column 1. Oh, that's what I said. I just didn't trust myself. Plus 5 times column 3. Right, so column 4 is a linear combination of 1 and 3. Yeah, right. And so column 2 and column 4 don't need to be part of this set because they're linear combinations of 1 and 3, right? So we can like recreate column 2 and column 4 if we wanted again using 1 and 3. So why include them there in the first place, right? In other words, column 2, and we saw this because they're not pivot columns. So column 2 and column 4 are not pivots, and they can be discarded by theorem 5. That's what the theorem tells us. And when we do that, we will then have a basis for the column space. So we're going to discard columns 2 and 4, and this will form a basis for the column space of A by theorem 6 above. But the key thing to note is we want to use the pivot columns of the original matrix. So we row reduced here and saw that we wanted column 1 and 3, but then we go back and actually use these two, right? So we get rid of this one, we get rid of that one, and we're going to use this one and this one. Right, so that's the last thing I want to write down here. Thus, a basis for the column space is obtained from the pivot columns of the original. So the original matrix A. In other words, column space of A in this particular case is going to be the span of the pivot columns. 1, 2, 3, 4, that was the first column. And then the third column is 0, minus 1, 2, 0. This is A1, A3. So, the column space equals the span of those things, or the other way to say that is, i.e., a basis for the column space would just be those two vectors. It would be 1, 2, 3, 4, 0, minus 1, 2, 0. Depends on the phrasing of what you want. Both those things are true, though. Okay, I think I'm going to stop right there. I'll just sort of summarize one more time what a basis is. A basis is a set of elements that spans the space and is linearly independent. So linear independence means the elements are boiled down to the most simplest form, and they span the space means that everything else in the space is a linear combination of those elements. And again, those are super useful. Basis is very, very useful moving forward because if you want to talk about a space, you can just deal with the basis elements because those represent the whole space rather than dealing with the space itself. Okay, thank you.